Hello, I'm Sérgio, and I'm going to present one of the research works that has been going on XAI, which is how can I choose an explainer and application-grounded evaluation of post-hoc explanations. This has been research done to evaluate explanation methods and explanation methods, particularly for human in the loop. So we're going to start off by motivating a bit about the problem that we have at hand. So for explanations, different personas have different objectives. Each one wants something different from explanations. So for example, a data scientist with explanations, they want to debug and iterate a given machine learning model. A human in the loop, which is someone that makes decisions based on the model score, the features, and explanations in this case. They want explanations to make better decisions. And a decision subject, which is someone that receives, that is affected by the decision. They want explanations to understand why some decision was made, and in the future, how can they improve their outcome. And as of today, there is no clear way and no standard way of evaluating and comparing different explainability methods. We have different methods, but we don't know for each case which one is the best. And for a given setup, for a given machine learning model, and for a given metric of target metric for our system, there is no clear way to evaluate these explainability methods. There has been a taxonomy that was introduced by Doshivalas and Kim that is about the experiments with explainable AI. These were divided in three different groups of experiments. The first one being with proxy tasks and simulated behavior of real humans. The second one is with real humans, but on simplified tasks. And the third one is on real humans performing a real task. So recapping, basically, the problem of this work is that the evaluation of XAI methods is usually done on proxy tasks or simulated users. The first two, mainly the first two types of evaluations that we've seen on the previous slide. We use metrics that are not related to the objective and to the user. Usually we use the desiderata to evaluate some kind of explanation, and it's not based on the user or the objective of the explanation. And we evaluate one XAI method, and we don't compare as different XAI methods at a single task or at multiple tasks, sorry. So the goal of this work is to evaluate and compare different XAI methods and their impact. And this impact is on a target persona, which is the human in the loop. To do this, we argue that we must do an application-grounded evaluation, which is with real humans and on a real task. So the solution for this problem, we named it XAI Test. And we broke down in 4 different steps this solution. So the first step is to define the hypotheses of our experiment. We formulate the hypotheses, and these are relative to the scenarios that we want to test. For example, we want to test if a given explainer improves the accuracy of the end users when compared to the other explainers, or if an explainer is better than having no explainer at all. Then we do the setup of the experiment, and in this part we define several questions related to the experiment. So who are the users of the experiment, how many there will be, what's the data, what's the model that we'll use, what are the variants, and which explainers are we going to use, questions like these. Here we also define the metrics that we're going to use to evaluate the experiment or the variance on the experiment. So for example, when making an experiment with human in the loop, we're gonna have to measure their performance, and this performance can be measured with accuracy, with speed, or we can even gather information about the perception of the user about the explanations that they're seeing. And based on these metrics and their distributions, we have to define the experimental parameters of the experiment. So we have to define the statistical test, the significance level that we want for our statistical test, the power, the effect size that we want to measure, which is like the difference on the distribution that we consider the minimum difference. The sample size for our experiment, and these are the basic parameters of an experiment. Then we run the experiment itself, and to run this experiment, we argue that we have to divide this experiment at least in three stages, or in three stages. The first one being only the information about the data. This can be like feature data or some more information that we have relative to the instances that the human in the loop is observing. Then we have information about model scar, and then we have the explanations. So it's in an incremental way. So if the first step, the user only has access to information about the instance that they are observing, and they make their decision based only on that, on the information that the instance has. Then we have the model scar. This usually is a number between 0 and 1, and numbers close to 0 represent a negative instance, close to 1 a positive instance. And then we have the explanations, which are based on the data and on the model scar, and try to explain why the model made a scar close to 1 or close to 0, or above a threshold or below a threshold. And then we go to the hypothesis testing based on the results that we gathered from running the experiment. So for each metric and for each hypothesis, we have to select the correct statistical test and check for significance. And then we can validate or reject our hypotheses, our initial hypotheses. So we ran an experiment, and this experiment was on a real world e-commerce fraud detection scenario. So what we had was three analysts, three in-house analysts. They used the usual review UI that they have to review transactions. And we used one model that was in production, which was random forest, a random forest model. With three different post-hoc explainers. And for this experiment, we used 1,300 transactions that were divided on the three stages of the XAI test. So for the explainers, we used these three explainers, mainly because they're used, they're commonly used explainers, feature importance explainers on the literature. And we used the tree interpreter also because this model is a tree-based model, and tree interpreter is one of the explanation methods that is usually used for tree-based methods. So on the UI, the analysts, additionally to the information for a given transaction and the model score for that transaction, which you can see here, they have information about the explanation. So the explanation would show the analyst based on the feature contribution that each explainer gave. It would give a list of features that were the most important for that instance. So feature contributions that features that contributed to to approve a transaction would have a green marker, and features that contributed to declining the transactions would have a red marker. Only the top 6 features with most contributions would appear on this explanation, and this explanation was basically indistinguishable between explainers. So each explainer produced the same similar outputs, and this was normalized in this way. So they were isolated between themselves with this type of UI. We used these were the size of the samples for each part of the experiment. So for data only, we used 200 instances, and for data plus the model score, we used another 200. And based on the information that we gathered from those instances, we calculated that for our power and for our significance level and effect size, we would need 300 instances for the explainers, and for each explainer we gathered 300 instances. We decided also on the metrics that we wanted to for our experiment. So for our notion of performance was on these metrics. So the first one was the time that the analysts used to decide the outcome of that transaction. The second metric was the accuracy that the analysts had. We had access to the labels of each transaction. Then we had the recall and the false positive rates of the analysts. To balance the recall and false positive rate metrics, we had similar sizes for instances with positive label and instances for negative label. We measured the user's perceptions also through questionnaires, and we wanted to see the opinion of the users on the completeness of the explanation, if it had all the information that was relevant for that decision, and the usefulness, either in time and in accuracy. So we asked if the explanation was helpful to make a faster review, and if it was helpful for making the review at all for the decision. Additionally, we have a final metric, which was on user agreement. So we reserved part of the sample to be reviewed by all the users, and we observed the agreement between the users on that sample. So if they made the same decision for those instances or not. To measure this, we use the FlySCAP. For the statistical tests, we observed that none of our metrics had a normal distribution, and because of that, for time we used the Kruskal-Wallis age test for when we were comparing more than 2 groups, and for binary variables, which were FPR, recall, and accuracy, we used the chi-square test. And when we had a comparison of 2 groups directly, we used the Mann-Whitney-U test for times and the Kolmogorov-Smirnov test for the questionnaire results, and the chi-square test for accuracy, recall, and FPR. When we were comparing 2 groups, this was usually done after a comparison of multiple groups, and because of that, we used a correction for the p-value. So the hypothesis for our experiment, the first one was that showing the model scar would improve the performance of the analysts when compared to only having the data. And what we saw was actually a decrease in accuracy, and this was significant. On the other metrics, we did not observe a significant difference. We also observed a decrease in time between data only and data+Model scar. So the analysts were faster reviewing transactions with the model scar, but they would have more errors. The second hypothesis that we had was that showing explanations would improve the performance over the variance of data only and data+ML model scar. What we observed was no significant difference between accuracy, FPR, and recall, but we did observe a decrease in time when comparing data only plus when comparing the data only with the data and explanations variance. So all the explanation methods, LIME, 3SHAP, 3Interpreter, and 3SHAP had better times than data only. The third hypothesis that we had was that different explanations have different impacts in performance. And what we observed was that one of the explanation methods, which was reinterpreted, have indeed a significant decrease in time when compared to the other explainers, more with LIME than 3SHAP, but 3Interpreter has a significant difference between the other two. It's not really observable in this graph, but it's because of the shapes of the distributions that made, and they are non-normal, that made this difference possible. The fourth hypothesis that we had was that each explainer was perceived differently by the analysts, and this was measured by the questionnaires. That was the objective of the questionnaires. On the first question, which was about the relevancy of the information, we did not observe a significant difference. On the second questions, we did observe a significant difference, and this was relative to speed. The analysts had a perception that the LIME was worse than the other explainers when it came to helping them decide faster. And on the third question, which was about helping them make a decision, the explanations from 3Interpreter were significantly different than the other two explainers, and the analysts had a notion that these would help them make decisions better. The last two hypotheses that we had for this experiment was that showing explanations increased the agreement of the analysts, and showing the scar would also increase the analyst's agreement. The obtained results were that did not confirm this and these hypotheses. So what we basically saw was that with control, the analysts had an agreement of 0.41. The agreement dropped dramatically when we added the model score, and then it came back to the original values when we added the explanations. We saw that the method that obtained better agreement was with LIME. We also made a small analysis on the explanations that we obtained for each explainer. So for each explainer, we observed how many features from the original data set did each explainer use. So we have these results. We observed that 3Interpreter was the one that created more diverse explanations. And it used 96% of all of the features on the data set to create the explanations for the 300 transactions that it explained. And LIME was the one that created the least variable explanations, with only using 30% of the explanations of the features on the data set. We also observed an overlap on the explanations, which means explanations that had the same features to explain the same instance. So we observed that 3Interpreter and SHAP were the ones that have the highest overlap, and LIME and 3Interpreter were the ones with the lowest overlap. What this means, what these results mean, is that the explanations that we had for each instance were highly dependent on the explainer that we had. They were not similar between explainers. Our study had some limitations, so we're going to talk about that in a bit. So the first limitation was of the sample size, and this was because of the constraint on the number of participants and their availability for the study. And because of that, the effect size was impacted, which means that we had a lower sensibility to smaller changes in distributions between variants. One thing that might have impacted this also is on the external factors. We could have external factors in our experiment that we did not account for, such as internet connection, for example. For one analyst, the internet connection could be bad in one day, and because of that, it might have had an impact in some of the variants. And this could be diluted, of course, if we have a bigger sample or a larger sample, or if we have some form of continuous evaluation of the explainers. And additionally, this was more of a constraint on the problem that we had. And because of the real world scenario that we were using on this experiment. So we used historical data, and we used an historical a setting that was the same as in the past. So because of that, we used transactions only from a given band on the model, which was a band near the decision threshold. And because of that, the task might be harder for the analysts, and it might be harder for it to create good quality explanations. And because of that, it might impact the performance and the quality of the explanations itself by using transactions from this band. The conclusions of this work was that we proposed a test, a framework for evaluating XAI methods. And this methodology is tailored for the human in the loop and for real tasks, which is an application-grounded evaluation, and it's agnostic to the XAI method that is being tested. This methodology uses task-related metrics, and it uses hypothesis testing and strong statistical analysis of the results. What we observed with the experiment was that there was a trade-off between speed and accuracy, and we observed that usually when the analysts took more time to decide, they would have a better decision. So, for example, in the case of data only, we observed the highest accuracy, but also the highest time to decide. And this is it for our work. If you have any questions, feel free to send an email to one of the authors of the paper. And thank you for being here.